Now let's look at the solution u as a function of x. And let's still set u1 equal to a known value. For example, for simplicity, let's set it to 0. But du dx, okay, let's set it to something, let's say a, okay, something known. What's interesting is that this boundary condition tells you nothing about the value of u on the left-hand side. So the value of u on the left-hand side, let me call u0, becomes an unknown. Becomes unknown, I have to solve as part of the finite element procedure. Okay, so I still have different. I still have a bunch of the same kind of basis functions. So the basis functions are the same. So this is my phi0, this is my phi1, this is my phi2, this is my phi3, and this is my phi4. But instead of having 1, 2, 3, instead of having n minus 1 unknowns, now I have n unknowns. I have one more unknown because the boundary condition I have cannot fix the value of the solution on the boundary. Okay, so we have one more unknown, which means we need one more equation, right? How do we get that one more equation? Any ideas? How do I get one more equation now that I have one more unknown, which is the value of the solution on the left? Well, if you look back into the finite element method, how do I get equations? How do I obtain these equations to solve? How do I actually get as many equations as unknowns? Well, I get the equations by substituting different functions into v, into the test function, right? I use, when I have n minus 1 unknowns, I substitute n minus 1 different test functions. I use n minus 1 different test functions to get n minus 1 equations. So when I get one more unknown, the only thing I need to do is to enrich the space of my test function, is to use one more linearly independent test function. And if we stick to the spirit of Galerkin method, remember that is to try to match the space of the test function with the space of the unknown, of the solution, right? That additional test function I want to use is what? Is phi0, right? I've been using phi1, phi2, phi3, etc., but I never used phi0. Now a phi0 becomes contributing to the solution. I also want to add phi0 in the set of test functions. Okay, so the test functions, the set of test functions now starts with phi0 and phi1, etc., to phi n minus 1. And my u now is also going to be a linear combination with I starts from 0 to n minus 1 of ui phi r. All right. Okay, one more thing is that my weak form actually now has to change. So previously, if you specify a boundary condition that is fixing the value, if you rederive the weak form, it won't actually change at all. But like if you look at the weak form with the derivative as the boundary condition, actually has an impact to the weak form. So here is one. Remember, our weak form is derived by integrating a test function v multiplied with the differential equation itself, right? So if d square u dx squared plus f equal to 0, then I multiply it with any v and integrate. It has to be equal to 0, right? Okay, so and how do we derive the weak form from this? We had to perform this thing called integration by parts. And from integration by parts comes a boundary term. The particular boundary term we have if we integrate this part by parts is v times du dx at 0 and 1, right? The value of this guy at 1 minus the value of this guy at 0. So that's the boundary term. And then we have a minus integration from 0 to 1. The v is put into one level of derivative, and a u is taken out one level. So instead of a square, I have just a du dx. That's what integration by parts does. Okay, and the remaining part is still copied. Integration from 0 to 1, v times f dx. This whole thing is equal to 0. In our previous example, because we didn't have as many degrees of freedom, so we can actually set our test function so that they are equal to 0 at the boundaries. But now, I mean, that way basically gets rid of this boundary term because v satisfies the 0 boundary conditions, no matter what value u has to be at the boundary, right? So as long as the values of u are fixed at the boundary, we know u does not have the degree of freedom at the boundaries, and we can restrict the degree of freedom of v at the boundaries and make sure they are 0. So we get rid of the boundary term in the integration by parts. But if we actually don't know what value of u is at the boundary, we need actually v to match the additional degrees of freedom so that we get as many equations as unknowns. And we can no longer get rid of the boundary part by setting v to 0. Okay, if u at 1 is still 0, okay, so let's say, but partial u partial x is equal to a at x equal to, sorry, I wanted to say that u1 is equal to 0. Yes, the derivative is set at x equal to 0. So the value is set x equal to 1, the derivative is set to x equal to 0. So we can still, the corresponding boundary condition for v is still that v1 equal to 0, but v0 is completely unknown, right? So v at 0 is unknown, which means we can only get rid of the boundary term at x equal to 1. So essentially what that turns out is negative of v at 0 times du dx at x equal to 0. So this is now my boundary term. Okay, I still have this the rest of this is still intact.